do chapter 6. We'll do 6 dash 139. Let me go find it. A heat engine operates between two reservoirs at 800 degrees Celsius and 20 degrees Celsius. 1/2 of the work output of the heat engine is used to drive a Carnot heat pump that removes heat from the cold surroundings at 2 degrees Celsius and transfers it to a house maintained at 22 degrees Celsius. If the house is losing heat at a rate of 62,000 kilojoules per hour, determine the minimum rate of heat supply to the heat engine required to keep the house at 22 degrees Celsius. All right, so we have a heat engine. It has a TH of 800 degrees Celsius, which is 1073 Kelvin. It has a TL equal to 20 degrees Celsius, which is 293 Kelvin. Okay. It tells us that half of the heat pump's power comes from heat engines. Okay. And then on the heat pump, we have a TH of 22 degrees Celsius, which is 295 Kelvin, and then a TL of 2 degrees Celsius, which is 275 Kelvin. Okay. They want us to find, oh, I missed the loss, sorry. There's a Q dot loss from the house of 62,000 kilojoules per hour. They want us to find what I have here is I have the minimum rate of heat supply to the heat engine. Okay, so Q dot H is the heat supply, HE is for the heat engine. Right, so this is the heat supply, heat engine minimum. All right, so let's draw our schematic. This one, I mean, it's always important to draw your schematic, but this one especially because it has a little bit more complexity, that without it, you can get lost in all the things you need to do. All right, so we have a heat engine, and we have a heat pump. We have the TH and the TL for the heat engine, the TH and the TL for the heat pump. So there's the Q dot H for the heat engine, Q dot L for the heat engine. So actually, I'm going to do this up here. Do that as that's the house. So we have the workout of the heat engine. Some of it goes somewhere else. Half of it basically goes to the heat pump, right? And we have our Q dot loss from the house. Okay, I think I got everything here. All right, so it's asking, this problem is asking for this, okay? Where do you want to start solving this? We're looking for Q dot H of the heat engine, right? Any ideas? So this is on the heat engine, right? So what can we calculate or have equations for or use for the heat engine? I got all day. Well, not all day, but I got part of a day. Work of the heat engine. Okay. All right, so the work of the heat engine, how would we do that? All right, so let's start with, I'm going to assume you mean from the thermal efficiency. So we have desired output and efficiency over required input, right? What's the desired output of a heat engine?
Work net out.
Yeah, the work net out. Okay. All right, what's the required input?
QH.
Yeah, so we got Q dot H, right? All right, so if we look at this now, we have an equation for the work of the heat engines right here, but we look through, we got an unknown that we don't know the value of yet, and the thermal efficiency we don't know the value, and ultimately the rate of heat transfer that we're looking for that heat engine, okay? All right, so that means if we want to use this equation to solve for it, we need to get the thermal efficiency and the work net out. How do we get the thermal efficiency? Is there anything that can tell us that?
Could we use 1 minus QL over QH?
1 minus QL over QH? Is that what you said?
Yes.
All right, so that comes from, this is from the COE on the heat engine. Work net out is QH minus QL, right? So if we look at the arrows, QH is going in, work net out is going out, QL. So the energy work out plus QL has to equal QH. If you rearrange, you get QH minus QL, right? So that divide by QH would give us this. Okay, we don't know then QL, right? And we're ultimately trying to solve that. Okay. Is there anything that could tell us the ratio of these two? Like QL over QH.
The COP?
That'll be on the heat pump, right? The calculator of the heat engine, the temperature of the reservoirs. Okay. So if you have reversible cycle, right? The ratio of Q dot L over Q dot H reversible is equal to TL over TH. Okay. So the ratio of heat transfers is equal to the ratio of temperatures when it's a reversible cycle. So that would make thermal efficiency of a reversible one 1 minus TL over TH. Okay. So that's the temperatures. So that we do have TL, we do have TH, but why can we use this? I know we determined we are going to use it, but why can in this problem use the reversible cycle for the heat engine? It did tell us and I forgot to write this down, the heat pump is Carnot. Okay, so this is Carnot, which is reversible. Okay, but it didn't tell us what the heat engine was, right? It did tell us something important down here in what it wanted us to find, this minimum, okay? The minimum saying that's the bounds, the best you can do, right? If you put in the least amount of, where can we put the least amount of heat into this heat engine to get this out? That would be with a Carnot heat engine, reversible heat engine, the best we can achieve. Okay, so when they talk about min and max and cycles, Carnot is what kind of creates that bounds. Okay, so that's why we can use this. Okay. All right, so then we plug in our values with our absolute temperatures, right? Okay, most common mistake I get is not doing that, not changing it to absolute. And then we get 0.727, which is 72.7%. Okay. All right, so that means since our cycle is reversible, we have this. Okay. So now we need to figure out work net out, right? And we actually have from the givens it's times 2, sorry. From the givens, right in the problem, it says half of the work net from work net out of the heat engine, which is this one, heat engine, goes to the heat pump. So that means we would have twice that value of what's actually coming out of the heat engine, right? All right, so now we have an equation for work net out, but we've added a new unknown. We have work net in now, okay? So we've figured an equation for this, but we've added a new unknown, okay? So now we got to get rid of that. How do we get rid of work net in? Okay, so we've come here, we've got work out, now we're to this point, right? With relationships. Any ideas? So we're now over here to the heat pump, right? So we can start doing the similar thing we did. Calculate temperatures of the heat pump reservoir. So we can do basically the same kind of setup we did, but on the heat pump side. So if we'll start with this COP. We have desired output of a required input. What's our desired output in a heat pump? Q dot H, right? We're trying to heat the house, right? So we want this Q dot H to be as large as possible, okay? So that's our desired output. What's our required input?
Work net in.
Yeah, so we're moving heat from a low temperature reservoir to a high temperature reservoir. So the opposite direction, heat wants to go, right? Heat wants to go from high to low. So to make it go from low to high, we have to put work in. So that's our required input. All right, so now we check what we have. Well, this is our equation that defines work net in. That means we got to figure out the COP of the heat pump, right? And we got to figure out Q dot H. Okay, so we got to figure out this one, and we got to figure out this one. All right, so we said, I heard the temperatures, right? So we can do the same kind of thing we did and use a reversible because it said it's Carnot already, right? So we can derive it again if we want. And divide by one of the Q's, QL or QH, and then the ratio of heat transfers is equal to the ratio of temperatures. So we have our COP heat pump reversible, since it's a Carnot heat pump. So we have TH divided by TH minus TL, which again, absolute temperatures, because you're dividing temperatures. Okay. We have TH, we have TL given in the problem, so we can solve, we get 14.75. Okay, so that means we have the COP. Okay, so the last we need to bound this problem is Q dot H. Okay, so if we go up to our schematic, we need the Q dot H of the heat pump. How do we get that?
Using the COP value and the Q dot loss that we're given.
Using the COP value? No.
That we just got.
We don't even have to go that far. So we just actually just look at the house. If we look at the house and we were to set up kind of a boundary on the house, Q dot H is equal to Q dot loss. Okay, so if we did CUE on the house, we can do open system conservation energy. There's no mass flow rate in or out of the house being shown on our schematic. So the mass flow rate's not carrying in or out energy. If we assume it's, I forgot to draw my assumptions. It's steady state. We're just holding steady at 22 degrees Celsius in the house, okay? Then it's steady state, that term goes away. There's no work in our boundary in the house. Okay, so all you have is the heat transfers. So that means Q dot H so Q dot H of the heat pump is equal to Q dot loss, which is 62,000 kilojoules per hour. Okay. All right, so that means we have bounds. We've bounded our problems, right? We have now Q dot, we can do it in blue too. We have Q dot H, we have COP of the heat pump, so we can use that to solve work net in right here. Go back, use work net in to get work net out of the heat engine. Keep going back up. We have work net out of the heat engine. We have the thermal efficiency, so we can use this equation to solve for our Q dot H minimum that's supplied to the heat engine, okay? So going through all that, we get 11,560 kilojoules per hour Okay. Any questions? No. Take the silence as a no. Is kilojoules per hour the same as kilowatt hours? No, kilojoules per hour is a rate. Kilowatt hours is actually not. So if you look at kilowatt hours, those are kilojoules per second times hours. So you can get rid of the units and just get kilojoules, right? Where joules per hour is a kilowatt, right? Wait, is that what you asked? Kilojoules? No, it's okay, yeah. Yeah, so you have rate here. The reason they use the kilowatt per hour is because it's the rate of your device. Let's say your toaster, your dishwasher, and then this is the amount of time you're operating it. So it's more of a simplification for people to understand that energy usage than for really engineers, because they understand energy versus rate a lot easier. But when you're talking about, okay, I have this device and I just run it for 8 hours or something like that, it's easier and then that energy costs some dollars or some cents per kilowatt hour. It's easier from that standpoint. Other questions? All right, so let's do 7-179. A 0.8 meters cubed rigid tank contains carbon dioxide, so CO2 gas at 250 Kelvin, 100 kPa. A 500 watt electric resistance heater placed in the tank and now turned on and kept on for 40 minutes, after which the pressure of the CO2 is measured to be 175 kPa. Assuming the surroundings to be at a 300 Kelvin and using constant specific heats to determine A, the final temperature of CO2, B, the net amount of heat transfer from the tank, and C, the entropy generation during this process. Okay, so we got a bunch here. All right, givens. We got a volume of the tank, 0.8 meters cubed. It's CO2. The initial temperature is 250 Kelvin. The initial pressure is 100 kPa. Okay, the electric resistance heater, they gave us the power, so it's W dot 500 watts. Right? It runs for 40 minutes, which is 2,400 seconds. Okay. And afterwards, we get a 175 kPa pressure. The temperature of the surroundings is 300 Kelvin, and we have constant specific heats. They want us to find A, T2, B, the heat transfer, and C, S-gen. Okay, let's draw our schematic. We have some electric power going in. We have some heat transfer occurring. CO2 inside here. Draw our boundary around the CO2. Okay. All right. So initially, let's do assumptions. We want to solve for T2, right? What can we do? Where can we start? All right, so we have substance, right? First off, figuring out what our substance is and how to get those properties, right? We have ideal gas, okay? So if we assume ideal gas, we have the ideal gas law, right? Which is P V equals mRT, right? And what is being held constant here? Volume, yeah. So we have, and obviously mass, because it's a closed system, and gas constant, right? So if we rearrange this, T over P is V divided by mR, that's constant for our problem. Right, so then we can just relate the two states, since this is being held constant during that whole process. Okay, and if we check, they gave us T1, they gave us P1, and they gave us P2, so we can use this to get P2. So we get T2, 437.5 Kelvin. Okay. So now we have part B is the heat transfer. Where do we start for that? Yeah, so COE, right? We have a closed system, so COE, closed system. Can neglect kinetic potential. We're looking for Q, so we'll just leave it where it is. So this is all we have is electric power or electric work. All right, there's no boundary work because boundary's not moving. Okay, pull the mass out of delta U. Okay, so let's go through this. Okay, so we're looking for Q, right? We got to get the electrical work. Okay, we got to get our mass, and we got to get our U's, right? So we start going through, right? Yeah, so mention mass. We have ideal gas law again. We have PV equals MRT, right? And if we set it up for mass, we have PV over RT. We have state one's pressure, state one's volume or temperature, and they give us the volume of the tank. We can look up R for CO2. This table A-1. Okay. So now we have PT, V, and gas constant. So we get our mass, which is 1.694 kilograms. All right, so mass is done. All right, how do we get electric work? All right. They gave us electric power in this problem, so how do we get the work? Yeah, we just use the rate times time, because they gave us a constant value for the rate, so that rate's staying the same over that whole time. Okay, so then that gives us equation for the electric work, because we have the power, we have delta T. Okay, so last is delta U. How do we get that? We have U2 and U1, right? So we've set up an equation for electric work. Now we need this. Okay. So this is the question, it's properties, right? So this is where you go, what type of substance do I have? And we assumed it's an ideal gas for CO2 gas. Okay, so we go and we set up and we look at our ideal gas section on our equation sheet, or how for ideal gases we get energy changes, right? So for properties for delta U, it's CV delta T, because they told us constant specific heats. For delta U, it's CP delta T, right? We need delta U. Okay, so that one. Okay, so let's put this all together. We have this, okay? We go through, the last unknown we have now is the CV. So we got to pull that from the table. So table A2B, T average, which is T1 plus T2 divided by 2. The CV is 0.706 kilojoules per kilogram K. Right? So then we got everything, right? We have our electric power, delta T, mass, CV now, T2, T1. So our last thing is heat, okay? The other thing I'll say is here, we got negative right here. And then when we put in our power, it's negative 0.5 kilowatts. And then we have our delta T here, right? And that negative right there is because it's work in, right? We're putting in this electric work. Right. So if then we solve, we get a Q of negative 975.8 kilojoules. And that negative right there tells us heat out. Questions? Okay. Remember, I assumed heat in right here because basically I have a positive sign instead of that heat, right? And we got the opposite of what I assumed. So it's assuming heat in there, it got negative, it's heat out. It's the opposite of what I assumed. With this negative for work right here, I'm assuming work out is the positive value. So if we solved this problem for work, it would have been, it was positive value, it would have been work out. Here, though, we have a work in we're putting in there. So that means we got to put the negative sign on the value we substitute for work in. Okay. All right, so now the last part is SGen, right? We need to figure out SGen. So where do we start to get SGen? Entropy balance, closed system. Yes. Okay. So SGen is in the entropy balance, right? That's where we entropy balance, closed system. Okay. So in our entropy balance, we have the what's crossing our boundary on the left. So this is crossing boundary. We have delta S, so this is inside our boundary. So this is the CO2 inside our boundary. This is how entropy can enter or exit in a closed system. All right, so, and then SGen just takes up the difference. That's why it's an entropy balance and not a conservation of entropy, okay? All right, so if we think about what we do have a heat transfer, right? So we have just one, the summation. We don't have to worry about the summation. We just have one heat transfer, okay? And we have the temperature that goes with it. We have SGen that we're solving for, and then we have mass times S2 minus S1, okay? All right, so if we look through this, we have a heat transfer. What temperature goes with that heat transfer? Okay, so this T comes from where the heat crosses the boundary. Okay. So if we go back up to our boundary, house temp, yeah. So that's what it's going to be, or the surroundings. If we go up to our boundary, you saw I drew it inside the tank, but we can do something like this and make our boundary rainbowy, but outside. Okay, just extend our boundary a little bit. Okay, so instead of it being where that green line is, where that rainbow line is right there, and that's T of the surroundings, right? This would have been what we don't know because it changes as heat is being transferred. It goes from T1 to T2, so it's not a nice set temperature if it's crossing the boundary right there. So we extend our boundary a little bit, okay? Because nothing's really going on with that air outside. There's no change. We can say it's staying steadily, or it's very minimal. So we have this T surroundings then, okay? so we have T surroundings. So that's the temperature at which that heat transfer crosses the boundary. If we had heat transfer on the other side, or you can have different heat transfers on your boundary, it's what that heat transfer goes along with that temperature. Okay, so any number of heat transfers, there'll be any number of temperatures. Okay, and you would have a Q over T1 plus a Q over Q2 over T2 or something like that, and in any number if you have multiple heat transfers. All right, so this, if we look at this, then we figured out our heat transfer in part B. We have the temperature of the surroundings. We're looking for SGen. We have the mass. So we got to figure out our entropies. All right, so where do we start, or what do we do for that? It's a property, right? So first off, we say ideal gas, right? Entropy is a property. S1, S2 are property. SGen, now that's not a property, but those aren't always related. S entropy 1, 2, it's not always related to SGen. Okay, so we have ideal gas. And if we go to our equation sheet, in chapter 7, we derived 3 equations for the delta S. Okay, and third one, all right, so the first 2 are constant specific heats. Bottom one is variable specific heats, if you want to be more accurate. It takes into account that specific heat changes with temperature. Okay. This problem told us use constant specific heat, so we got to use this one or this one. Okay. If it didn't tell us, we could assume variable specific heats or constant specific heats throughout the problem. So I got second equation. There's actually no wrong answer on this one. Okay. So you are right, or the first one is also right. Okay. It just depends on what you have. We were given temperatures. We were given we were given T1, we solved for T2, so we could use either of those. And then we're given pressures, okay? What if so we could use the second one, right? We have temperatures, we have pressures, we have to go get CP. What if we use the first one with CV natural log T2 over T1? What happens with the natural log of V2 over V1 in our problem? Goes to 0. Yeah, because in this one, it's the natural log of 1, since V2 is equal to V1, it's constant volume, right? So that cancels, right? If you had a constant pressure process, it would cancel on the other one, right? So both of these would work. This one, we have CV, so we can use this one without just the first term, okay? So let's substitute everything in. But both of them will give you the same answer if you do it correctly, okay? If you substitute them in, there's no wrong way. All right, so we have T surroundings. We have mass, and then all we need is that first term, CV. Okay, so if we look through this, they had us solve Q in part B. We have T surroundings. We're looking for SGen. We have the mass. We have CV. We have T1, and they had us solve for T2 in part A. So all they really had to ask us is SGen. We would have had to go solve for Q. We had to go solve for T2, but they kind of helped us and stepped us through the problem. Okay. All right, so the only unknown is SGen. So we can rearrange, plug in our values, again, absolute on temperature. And we get 3.92 kilojoules per Kelvin, okay? Any questions? Could we have used, can the S naught, so you can see how it relates, the variable specific heat just replaces that CP natural log T2 over T1, makes it more accurate. So you can use the S naught from the tables for CO2, but you got to be careful. The tables for CO2 is kilojoules per kilomole. So everything except for air has a kilojoules per kilomole. You'd have to use a molecular weight to get it in kilojoules per kilogram for this S naught, or it's kilojoules per kilogram Kelvin, right? But it's in those tables, it's kilojoules per kilomole Kelvin. The air A17 actually has kilojoules per kilogram Kelvin. So that's the only thing to be careful of if you don't use constant specific heats for anything that's not air. The tables are just for moles when we get to chemical reactions. Any other questions? All right, so last, I'm not going to get off that easy. We got to do some diagrams. All right. All right, for the TV and the PV diagram, what's being held constant?
Volume.
Volume, right? So volume's constant, force yourself, it's a vertical line. So you're either going up or down, right? And in this case, we have temperature, we have pressure. So we know we're going up in temperature, up in pressure, right? That is a beautiful vertical line, right? All right, so we have T1 to T2. And we have our pressure. So this is oops, me rushing. That should be labeled as pressure. This is temperature. Okay. Now, the TS diagram. Volume is being held constant, but we have a TS. So that means we got to figure out, are we increasing, is the entropy at state 2 greater than the entropy at state 1, or is it less than? Okay. S2 is greater in this case, and it doesn't have to be greater, even with SGen. Okay. And we can check this right here. So all we're plotting is this. That's delta S, right? SGen isn't always equal to delta S because you got this heat transfer. When there's heat transfer there, you could have a negative delta S and the heat transfer takes up the difference that still creates an SGen that's positive, okay? SGen is a different term than delta S, okay? So I know students get that one confused, okay? Sometimes they are related, right? If it was adiabatic, this Q over T goes away and SGen gets related to the delta S. All right, so that's, any other questions on that one?
Wait, so how did we know it was increasing? I'm a little lost on that part.
We can just calculate it from this, from CV natural log T2 over T1, and that would give us a positive delta S. Because that's all we're plotting is the property of S. So we could just
Oh,
use,
okay, I see.
we could just use these equations to figure it out, right? We also, it's typically, I don't have you guys memorize it, but that's the constant volume line too on a TS diagram, because V is constant. So it goes in this steep slope that way. Okay. questions? All right, let's do 7-184. An adiabatic capillary tube is used in some refrigeration systems to drop the pressure of the refrigerant from the condenser level to the evaporator level. R134.2A enters the capillary tube as a saturated liquid at 70 degrees Celsius and leaves at -20 degrees Celsius. Determine the rate of entropy generation in the capillary tube for a mass flow rate of 0.2 kilograms per second. All right, so we have R134A, it's adiabatic, and it's a capillary tube, but we'll see that in the schematic. Okay. Initially, it's a saturated liquid, state 1, so that's quality of 0, sat liquid. Temperature is 70 degrees Celsius. Exiting temperature is -20 degrees Celsius. And then they give the mass flow rate, 0.2 kilograms per second. They want us to find the rate of SGen. All right. So we have our capillary tube. It's just a very small diameter tube that creates a restriction. We said it's adiabatic. And then we want our boundary. All right, so where do we start? Entropy balance, open system, yes. Okay, so we're looking for SGen, right? Rate of entropy, in this case, we have mass crossing our boundary, it's an open system. Entropy generated is always entropy balance, and then we have open system mass is crossing our boundary, and it's rate form. Okay, so entropy balance. Open system. Oops. Any questions? Glenn, I'm gonna mute you, Robert, because you got it off. You're not on mute. So an easy way just to remember, and maybe your other instructors have told you, is to stay on mute, but you can press the space bar when you want to talk. So it's an easy way to just talk with the space bar down and then release the space bar and it goes back to mute. So that way we don't get any weird noises. I don't hear anybody's dog or anything. You only get to hear mine with those kind of things. So that way, and you can always get some weird interference at times too. All right, so we have this, right? Our open system entropy balance. What can I cancel?
Can we assume steady state and cancel the sum of mass in and out?
Steady state. Yeah, okay, so we have steady state. right? And then it's adiabatic, right? There's no heat transfer. There you go, thank you. And then I heard or saw conservation of mass, right? So RCOM. So we only have one inlet, one outlet, so the mass flow rates are the same. So then we put that together. We have mass flow rate S1 minus S2, rate of entropy generation equals 0. Okay. So we're looking for the rate of entropy generation. They gave us mass flow rate. We got to figure out our entropies. How do we do that? Table, question mark? Oh, sorry, that's how I read it, right? Table? So yes, right, we have refrigerant, right? So we got tables, right? So let's do our states. All right, so state 1, we have a quality of 0, and a temperature 70 degrees, okay? All right, so our state is fixed, right? It's saturated liquid. We can get anything we want, anything our heart desires, right, at that state. So we can get S1, because that's what our heart desires. Right? And we want 0.53763 is what our heart ends up with. Okay. We get volume. We'll see. Let's see. We got state 2. They gave us temperature, right? It's -20. So then maybe this is what you're getting at. We need another property, right? To fix our state to get it from the table. So where it's not actually volume in this case. Okay, so it's any other ideas? Anybody? All right, so we're unsure. Let's do our COE. Open system. All right, so we have this. Let's simplify this. Oh, it says enthalpy, and that is what we're going to end up with. But what can we cancel here, right? I'll cancel what we've already said. Adiabatic, right? So there's no heat transfer. It's steady state, right? So we've used that one. So we still have easy one. There's no change in potential energy, right? So the tougher one is, I mean, it's not as tough with the capillary tube, but there's not going to be much change in velocity from the inlet to the outlet. Okay. So the areas are pretty similar. So you get to neglect the kinetic energy too. So yeah, no work. There's no work, right? Okay. All right. So we have mass flow rate carrying in enthalpy, mass flow rate carrying out enthalpy, right? So conservation of mass pulls the mass flow rates together. If we divide by mass flow rate, then we just have that H, where H1 equals H2. And this is an isenthalpic process. And we'll be using this a bunch in refrigeration cycles. This is like a expansion valve. Okay, so it's a cheap expansion valve is a capillary tube. Is this? Okay. All right, so that means we come back up here, we have enthalpy 2 is equal to enthalpy at 1. Okay, so we can get the enthalpy at 1. All right, now we have enthalpy at state 2, okay, and we have temperature. Okay, so if we check, we're going to find, we check the enthalpy, we're going to see that our enthalpy is greater than the saturated liquid value at -20, but it's less than saturated vapor value, so it's a sat mixture. Okay. So we can use this equation to get quality at state 2. And then use the same equation like this, but with entropy to get S2. Okay, so we have S2. So now we come back up. We have S1, we have S2. Our only unknown is the rate of entropy generation. So we can substitute and solve. We get 0.0166 kilowatts per Kelvin. We can always also do our TS diagram. And we know we are saturated liquid at state 1, and we go to a saturated mixture at state 2, and our temperature drops, right? All right, so state 1, saturated liquid, right? And then we have a quality. State 2, and this is our H2 equals H1 line, right? And this is pressure 1, this is pressure 2. Pressure 1 is greater than pressure 2 in this case. Okay, so we're dropping pressure through this small capillary tube, and we drop pressure, we drop temperature. Okay. All right, in this case, the only place we didn't have any heat transfer, so the S-gen was related to the change in entropies from the inlets to the outlets, right? And since we had an increase, we had a positive S-gen, there was no heat transfer to take any of that entropy in or out of the system, it had to go into the outlet state. So state 2 is greater than state 1. There's a dome because it's the dome is for R134A or water in our case, because that's what we have for properties, but the dome is there for latent energy, right? If we're changing phase. So because have liquid, we have some vapor, so that's why when we use the dome, right? Because we could have hundreds of different property tables, but the book only prints us the 2, right? But there's many different, and every substance has a dome. It's just what temperature does it occur, right? So even CO2 that we talked about in the last problem does have a vapor dome. It's just at a much lower temperature. So we're using it above where that vapor dome is and where it behaves more like an ideal gas. Okay. Hopefully that answers your question and didn't confuse you. But for our book, when we have water or refrigerant, we have that dome. Other questions? So the last one, when we did our diagrams, we assumed ideal gas. Ideal gas does not have a vapor dome. If it's ideal, it means it doesn't ever condense when we assume it's ideal. Okay. The specific volumes are not the same from the inlet to the outlet state. Okay, so that would not end up being the correct, you wouldn't get the same value. Okay. I think the constant volume line goes up or something different. Okay, so you can't have 2 properties being constant, right? I just totally nailed it. All right, you can't have 2 properties being constant. So enthalpy is constant, so then the other is changing, right? You couldn't have volume and enthalpy be constant. If they're constant, then they're at the same point. Okay, if they're both constant, you're still at state 1. Okay. Because that's 2 independent intensive properties. All right. Other questions? Hopefully everybody's getting some of this or understanding some of it, because I'm hearing or seeing comments from only a few, which is typical even in class. So I hope you're answering and following along and answering the questions that I pose if you don't want to say them out loud to yourself, and then understanding my explanations as we go through. If you don't want to pose those questions to the group, please, we can set up a Zoom and talk through some things. This is the time to review and to understand Thermo 1. So then when we start doing new stuff, you know that stuff really cold, you know it really well. So then the new stuff is what you're learning and not the old stuff. Okay. All right, then that's it for today, unless you guys got some other questions. Will you post PDF file for your work? So what I just created is what you're looking for. I mean, I have this is the only work I have, so I haven't created other notes for this class other than what we just went through. There is no other notes. I just have the solution manuals to grab the answers, like the final numbers from. I don't go about the processes always the same as the solutions, because I don't necessarily always like it because I skip steps and go about a path I'm not always a fan of. So what you see you might have better notes than me. So yeah, it's in the recording, basically, the posted. You can just scroll through and see my work and see the explanation. And you actually see a better explanation when you have me talking through it than just the words on the paper. The words on the paper. Okay. Any other questions? All right. Well, and that's it. Have a good rest of your week, everybody. I'll see you on Monday, right? And then unless you guys have questions and want to contact me. All right. All right. Have a good one.
Thank you, Professor.
This is Nerd.